and C. C is completely outside the set S, and A and B completely inside the sets. Okay. So this is our conventional set without any ambiguity, without any doubt like that. This is also a crepe set or conventional set, but there is a doubt when we consider the line segment D. See that the line segment D is partially inside the set or partially outside the set. And here is a question: is D belongs to the set S or D does not belong to the set S? So this is a big question. But in our conventional set theory, we never dealing with this kind of situation, partial belongingness. So we can say that D partially belongs to the set S. But our conventional set theory, this kind of situation, I am repeating this statement again, this type of situation we never consider. The question is how this kind of situation can be represented in a mathematical form. If an element partially inside or partially outside. So in this situation, we cannot say S is a or D belongs to the set or D does not belong to the set. So is it a crypt set? The answer is no. As per our conventional definition, the collection of A, B, and D is not our conventional set. We cannot represent G as a member of S or not a member of S. So this is not our conventional set or the crypt set. So similarly, we consider another elements, say A, B, like that. So for convention, we consider that the 50% of the line segment D is inside the set and 50% is outside the set. For line segment A, 25% is inside the set and remaining 75% is outside the set. And for the line segment E, 75% inside the set and 25% outside the set. So if we consider all this line segment and if we try to distinguish about the belongingness of the line segment, then we can say that D is 50% inside the set, F is 25% inside the set, and E is 75% inside the set. And A and B fully inside the set. That means you can say that A is a 100% member of the set S, B also 100% member of the set. And what about C? C fully outside the set. That means you can say that C is 0% member of the sets. So if you introduce this another parameter along the elements of the set A, B, C, D, E, F, these are the elements, and along with these elements, if we consider another number means the amount of belongingness. So A and B are 100% inside the set. So 100% is a member or a number associated with the element or line segment A and B. 50% is a number which is associated with the line segment D. Similarly, 25% for A, 75% for E, and 0% for the line segments. So if you consider two terms, the element and their percentage of belongingness or degree of belongingness, then we can represent this entire elements A, B, C, D, E, F all constitute a set S with certain degree of belongingness, and this kind of set is called the fuzzy set. Okay, so all the elements A, B, C, D, E, F, all line segments are the member of S with certain degree of belongingness for the set S. So this is another concept. So one is that kind of the belongingness of the line segment is into the set degree of belongingness. So in our conventional set theory, just we are writing the name of the elements with a set. But in fuzzy set, we write the name of the element as well as the degree of belongingness of that particular element with a set. Okay. So this is the concept of the fuzzy set. So another example we are considered here. Here we have 5 classes, G1, G2, G3, G4, and G5. Initially, all the classes are empty, and this is the first class G1 is filled. So certain percentage of the entire class is filled by some liquid. So we can say that this is a 20% filled. So we can say that the glass G1 is filled 25% of its full length. Or we can say that the glass is not filled 75% of the entire amount. Similarly, G2 is filled 50%, G3 is filled 75%, G4 is filled with 80%, and G5 filled with the liquid 100%. This is 100% filled up. Okay. So if you consider the filling up of the glasses, then you can say that the G1 is a 25%, means 20.25. G2 is filled up 50%, means 0.5. That means the percentage is converted to a unit interval, 0, 1 unit interval. So the 25% means in the unit interval 0, 1 it is 0.25. 50% means it is 0.5. So the amount of filling of the glass, filled up amount of the filled up of the glass by some liquid can be represented by some degree or some numbers. So we can say this, or we can write up the entire picture, entire diagram by this kind of representation that one written in filled up. Say it of filling up of the glasses. So all the glasses except the 5G5 are partially filled. So that partial thing can be represented by its degree of filling. Okay, so this is another concept, another kind of concept of the physics. So I think the better first one is the better representation. If a line segment is partial inside the set, then how we represent this kind of set. Okay. So this is a mathematical representation or mathematical definition of the fuzzy set. In our conventional set theory, we consider one universal set and consider another subset like that. So here we consider capital X be a collection of object, all object. Okay. Sorry. So capital X is a collection of all objects we have considered here. Yeah. Capital X is the collection of all objects, and capital A is basically a subset. We are trying to define a subset A of the universal set capital X. That subset A is denoted by this one, xi is the element, and mu a xi, where mu a xi is called the degree of membership or simply the membership value. That means basically this represents the amount of belongingness of the element xi to the set A, and that one is denoted by mu a xi. Okay. So xi is the element, A is the set, and mu a xi represents the degree of membership value, and that value is lies between 0 and 1. If it is 0, then that means we can say that the element xi is completely outside the set. And if it is 1, mu a xi is 1, then we can say that the element is completely inside the set A. And if it is lies between 0 and 1, then that particular element is partially belongs to the set A. So this is the mathematical representation of the fuzzy set. And the membership value should be lies between 0 and 1. I have already mentioned here. So our previous example means the collection of the line segment. So S is the collection of the line segment, and that one is denoted by capital S, is a fuzzy set, where A comma 1 means the line segment A was completely inside the set S, so its membership value is 1. Similarly, B comma 1, B is completely inside the set, so membership value is 1. C comma 0, that means 0 means it is completely outside the set, but we have considered here the C is also the element of S. So this is the one advantage to represent the fuzzy set. That means all elements, whether it may be belongs to the set or completely belongs to or partial belongs to, all elements can be written within the sets. So D is 0.5, means D is 50% member, E is 75% member, its membership value 0.75, F is 25% member, which its membership value is 0.25. Okay, so this is the representation of fuzzy set. This is the one kind of representation of fuzzy set. Okay, but one convention is that if the membership value of an element is 0, then we generally drop out that particular element. we only consider that element whose membership value is greater than 0 and up to 1. Only we consider those element, or we represent those particular element uh, to for simplicity of the sets, or to write in simple form. Now about the graph. What is graph basically? So some computer science students or some student who are studied mathematics from say Calcutta University, pure mathematics, or some other universities, they are studied in their PG courses what is graph. Also some universities taught graph theory in UG level under the discrete mathematics. So graph theory is not completely the unknown subject for the participant. Some people knows what is graph. So this is a example. This is a diagrammatic example of a graph. So in this diagram, what's are there? There are A, B, C, D. Some circles are there, and inside the circle, some alphabets are there. No? A, B, C, D, like that, and some straight lines or curved line are there. So all the circles, it may be dot, it may be failed circle or empty circle like that, but it may be dots. Some dots we generally called. So A, B, C, D, E, F, G are the vertices, and the line segment A, B, B, C, C, D like that. These are called the edges. That means a graph is basically the combination of two sets. One is a set of vertices and another is a set of edges. It is for our conventional graph. The set of vertices and set of edges are the certain sets, the classical sets for the classical graph theory. So a graph is nothing but the combination of two sets. One is V, set of vertices, and another set V is a set of edges. But there is a relation, basically a relation from V to E. So based on some relation, we can generate different graph for the same set of vertices and same set of edges. So here A, B, C, D, that means the circle represents the vertices. Generally vertices are represented by circle or dot. It may be a filled circle, it may be empty circle like that. And the edges are generally drawn by the straight line or curved line like that. So here the set of vertices are generally and widely represented by V, and the set of edges is generally denoted by E. And this combination V comma E is nothing but the graph. G is A equal to V comma E. This is the conventional notation. Now the question is what mean actually the vertices? What does mean the vertices? But in reality, the what is the meaning of vertices? What is the meaning of edges like that? So for this purpose, we have considered here some examples. The vertices may be some cities in a particular district or a particular state or particular country, or even the cities in the entire world. The cities may be taken as the vertices. Okay. Some colleges, some universities, colleges and universities combinedly we can consider as a vertices of a graph. People in a Facebook or people in a WhatsApp, the members of the WhatsApp or Facebook, it may be as a individual person or a group of people, that is Facebook group or WhatsApp group, may be considered as a vertex. Even variables in a computer program, the programs variables which are used in a computer program may be taken as the vertices, and many other things. That means depending on the example, we consider the set of vertices, or we can identify the set of vertices like that. Similarly, what are the edges? The roads connecting the cities can be taken as the edges. The faculty interactions between the colleges, between the universities, between other peoples can be taken as the edges. The interaction between the faculties or other peoples or officials, vice chancellor, directors, principal. If there is an interaction between the uh, any two members of a college of two colleges, then there is an edge between the colleges like that. Simultaneous activeness of program variables. If you consider the variables of a program or the vertices, then if two variables are simultaneously active, then we may draw an edge between the variables. So this is a very interesting thing. That means for any kind of computer program, any C program or C++ program or Python program, for a particular program, we can draw a graph. And by solving the graph problems, we can solve the original problem. For example, for a particular computer program, we to execute any computer program, we use some registers. Okay, we use the memories, particularly the register, and you know that the register are very expensive. So to minimize the number of register, we can construct a graph for a given computer program. And by solving the graph coloring problem, we can find out the minimum number of registers which are required to execute a particular program. So the graph theory or graph coloring may be used to solve the register allocation problem. So this is a very famous problem which is used in a graph computer design or computer architecture. Okay. Now another parameters are also associated with a graph. That means the weight on the vertices or weight on the edges. Weight is another parameter, a very interesting parameter which are associated with the graph. That means the weights of a graph, it may be associated with vertices, or it may be associated with the edges. That weights may be the road distances. Distance between the cities represents the weight of the road. The travel time from one city to another cities, the travel time may represents the weight. It may be the travel time by train or travel time by buses, travel time by flight, like that. The travel time may represents the road distance, distance between the cities, or distance, uh, sorry, travel time may be used as the weights of the connecting cities, like that. Frequency of interaction between the faculties of two colleges or two universities or two institutes represents the weight of the age. Timing of activeness. If you consider the computer program, then the timing, the duration of activeness of the variables may represents the weight. Okay, so these are the example which are coming our everyday problems of the example of graphs which are coming in our everyday life. Each day, every day we are using the Facebook, WhatsApp, like that, in interaction with the faculties of the between the colleges or in institute, like this. So these are the few example of vertices, edges, and weights which are associated with the graph. Now it is very interesting things is that the graph theory is a subject. Note that the graph theory is a subject. It may be a subject of mathematics, or it may be a subject of computer science. So graph theory is a subject which is studied in two different directions. One is algebraic graph theory and another is algorithmic graph theory. Okay, this is the very interesting thing. These two directions are completely different. And it means algebraic graph theory is studied in algebraic graph theory, one direction of the investigation or study, and algorithmic graph theory is completely another direction of the investigation or study of this subject. So in algebraic graph theory, people are trying to investigate some properties of the graph. That means in algebraic sense, that means they are trying to find out the parameters, the upper bound and lower bound of the parameters. So to study the algebraic graph theory, thus basic mathematical knowledge is sufficient. So lot of people know, basically some people of our states are working on algebraic graph theory. Those who are from mathematics background and studied the graph theory, mostly they have studied algebraic graph theory. Okay, but in algorithmic graph theory, generally we are trying to design some algorithm to find out the exact parameter of a given graph. So we have to design the algorithm, and for this purpose, to study it in this direction, we have to know the basic idea of data structure, design of algorithm, and memory allocation. So these are the few topics which are completely associated with the computer science. So if you have this basic idea on data structure, computer memory organization, basic idea of memory organization, yes, you can study on this area, particular area, algorithmic graph theory. So generally the mathematics people are working on algebraic graph theory, and computer people are working on algorithmic graph theory. Okay, so these are the completely different directions. But any people from mathematics background, they can work on the algorithmic graph theory also. There is no hard and fast rules. So the mathematics background people can work on algorithmic graph theory by knowing the basic principle of data structure, basic principle of algorithm design, and basic principle of the memory allocation. So my PhD actually on algorithmic graph theory. But another thing is that the algorithmic graph theory as well as algebraic graph theory, both the direction is studied for the Krebs graph. That means our conventional graph theory, as well as these two directions are also studied on fuzzy graph theory. Okay. Lot of papers are published on fuzzy graph theory in algorithmic sense. That means the basic definition, basic applications are available for fuzzy graph theory in algebraic sense. That means some people from our South India, Pakistan, China, USA, Sri Lanka, and many other countries, they are working on fuzzy graph theory. But most of the people, 95% people, are working on algebraic graph theory. Fuzzy algorithmic graph theory, sorry, algebraic graph theory, fuzzy algebraic graph theory. Very few person are working on fuzzy algorithmic graph theory. So there is a very big area for research on algorithmic fuzzy graph theory. So recently I have published one book on modern trends in fuzzy graph theory, and that book is published by Springer. And in that book, we have mentioned that the theory on the fuzzy graph theory and application, a lot of application, real life application. I mentioned that we have defined the actual problem, real life problem, and then we have give some outline to solve that particular problem, and some little bit algorithm we also developed there, or we have designed some algorithms to solve the real life problem. So this is the direction, completely direction of study the graph theory. So I can suggest our new researcher to work with this graph theory. Either it may be algebraic graph theory, or it may be algorithmic graph theory. It may be for Krebs graph or conventional graph theory, or it may be fuzzy graph theory. So lot of scope are there to studied the graph theory. See that the graph theory is basically very old subject, almost 300 years old, because the first real life problem was solved by Euler in the year 1736. 1736. So this is almost 300 years old problem, but even it is young due to its wide application in our real life or daily life problem. So graph theory is very modern subject, we can say. But the fuzzy graph theory, on the other hand, the fuzzy graph theory is only 55 years old. This one developed on 1965 by Professor L.A. Charlie. So the fuzzy graph theory is the 55 years old. So this is the very new direction, fuzzy mathematics and graph theory and combination of mathematics, fuzzy mathematics and graph theory, that means fuzzy graph theory. All these are the very new directions of the for the research. So young researchers can start their work on the fuzzy mathematics and graph theory. So by fuzzy graph, see that the fuzzy graph and our conventional graph both are same. Structurally both are same, diametrically both are same. But when there is an uncertainty, when there is an uncertainty, so that they are uncertainty on vertices and on edges, then there is a separate graph theory, and this particular graph theory is called the fuzzy graph theory. Okay, when the uncertainties are occur in the on the vertices and on the edges, then we consider the fuzzy graph theory. Otherwise, the Krebs graph is sufficient. If there is no uncertainty, there is no role of fuzzy mathematics or fuzzy graph theory. If there is uncertainty, a particular type of uncertainty, then we use the fuzzy mathematics. Okay. So this is a very simple example of a fuzzy graph or fuzzy networks. So a lot of peoples are there. So you can say that this is a small portion of the WhatsApp or small portion of our Facebook. A lot of peoples are there in the entire diagram. So these are the some persons, and each person is a vertex of a graph. And if there is an interaction between two persons, there is an interaction between two persons, then there is an edge. Okay, so there is an interaction between these people and with these people, so there is an edge. And there is no interaction, so there is no edge between these two people. Okay, and there is a number associated with each people. See that a number is associated with these people. 0.25 means this particular people appears in a Facebook or WhatsApp, whatever may be this diagram. He or she appears say 25% in a day, 25% time of a particular day or particular time interval. So depending on the appearance or the presence in a particular networks or whatever, or so WhatsApp or Facebook, depending on the interaction or presence of a particular networks, we determine the degree of membership of the vertices. And depending on the interaction between two peoples in a particular time intervals, it may be a particular, it may be a single day, it may be a week, it may be a month, it may be a years. So if you fixed up a time interval, say t is the time duration, it may be 1 week, it may be 1 day, it may be 1 month, it may be 1 hour. So within that particular time interval, the number of intersection or amount of intersection represents the degree of the edges. Okay. So it is generally happens that we are not interacting between any two peoples. In general, we are not interacting for all times, no, throughout the day or throughout the month or throughout a particular time interval. So every time we measure the amount of interaction to determine the age membership value. So the age is not certain. Connectivity between any two peoples are not certain in a fuzzy network or the WhatsApp or any kind of social networks. The interaction between any two peoples not possible throughout the time interval. So this is basically a fuzzy network, uncertain networks. So WhatsApp, our Facebook, our ResearchGate, our Twitter, all the social networks are nothing but the proper example of the ideal example of the fuzzy graph. Now, there are a lot of applications of graph theory as well as fuzzy graph theory in our real life problem or real world problems. So some of them are highlighted here. The communication network, that means internet, mobile, these are the nothing but the graph theory is the backbone of the of all kind of communication networks. So internet, whatever may be, uh, any computer or any say computer communication device, all these devices can be taken as the vertices, and the connection, physical connection or logical connection, can be treated as the edges. So internet communication, mobile communication, military communication system, all this communication system is modeled by the graph theory. Social networks, nowadays the social networks are very much familiar with every people or most all people. So Facebook, WhatsApp, ResearchGate, Twitter, LinkedIn, all are the example of graph theory. Particularly, we can say that the social networks is nothing but a fuzzy graph theory. In the city planning, road planning, or any kind of train line construction, road line construction, all these things are depends on the graph theory. Traffic line signaling, that one is nothing but the graph coloring problem. Transportation system, DNA studies, and many other things are the subject of graph theory. Similarly, the isomorphism, testing of isomorphism of chemical compounds are the subject of graph theory. That means using the graph theory, we can solve these problems. So in fuzzy graph theory, see that in our conventional graph theory, there are two sets. One is set of vertices and another was set of edges. But here in fuzzy graph theory, that set of edges is replaced by these two functions, sigma and mu. Okay. So sigma is a function from set of vertices to interval 0, 1. So interval 0, 1. Similarly, mu is a function from the set of edges. V cross V means nothing but the set of edges. Okay. Any element of V cross V. This is a Cartesian product. So any element of V cross V as a is an edge. Okay. So mu is a mapping from any set any edge to the unit interval 0, 1. That means we can say that the sigma is associated with each vertex. That one represents the degree of appearance or degree of membership of the vertex. That means sigma x is the membership value of the degree of membership of the vertex x into the graph. And mu of xy basically it is from v cross b. So mu of xy is the degree of membership value of a particular edge. And each membership value lies between 0, 1. And 0 and 1. Membership value should be lies between 0 and 1. Okay. So it is a positive quantity between lies between 0 and 1. And this condition must be satisfied for the graph theory, fuzzy graph theory. That means the mu of xy, that means the membership value of the edge xy. This represents mu of xy is nothing but the membership value of the edge xy, which is less than or equal to minimum of the, what is sigma x? Sigma is the degree of membership of the vertex x, and sigma y is the degree of membership of the vertex y. So minimum of sigma x and sigma y is the more than the membership value of the edge xy. That means xy is an edge and x and y are the end vertices. Okay. So the membership value of the end vertices x and y is more than the membership value of the edge membership of the edge joining the vertices x and y. So this condition should be satisfied for each pair of vertices. Okay. So this is the limitation or restriction for fuzzy graph. Now this is the conventional representation or diagrammatic representation of a graph. So A, B, C are three vertices. The number associated with A, that is 0.7, represents the degree of membership of the vertex A. B is its membership value is 0.6. C, its membership value is 0.8. That means A, B, C, the vertices which are not present every time. If we consider T is the time duration, then A, B, C, all these vertices never present during the time interval T. It may be present for 70% time. The vertex A presents 70% of the whole time. B presents 60% time within the time interval T. C represents the 80% time duration. That means they may or may not be present in a particular time instant. So this represents the membership value. And the numbers associated with each edge represents the degree of membership value of the edges. So for the edge AB, the membership value is taken as 0.45. That means the degree of membership value is 0.545. Membership value is 0.45. That means the membership value of edge, this one. That means this edge may or may not present during the time interval T. Similarly, the membership value of the edge BC is 0.5, AC is 0.6. So these are the membership values associated with the vertices and edges. In our conventional graph theory, the membership value of each vertices, each vertex and each edge is 1, exactly 1. That means they are always certain. In the conventional graph, vertices and edges always certain. That means they appear for all instant of time interval T. They are not uncertain. So there are different types of fuzzy graphs are there. Type 1 fuzzy graph means crisp vertex set and fuzzy set. That means vertices are certain and the edges are uncertain. This is one kind of fuzzy graph. Type 2 fuzzy graph means crisp vertices and edges. Both are certain. Vertices as well as edges both are certain, but the connectivity is uncertain. So this is another kind of fuzzy graph. Fuzzy vertex set and crisp edge set. This is a different type of fuzzy set, and if this condition or this type of fuzzy graphs are appears in our picture or in our real life application, then this is called the generalized fuzzy graph. So this is rarely happens in our real life situation. Type 3 fuzzy graph. Type 4 is crisp graphs with fuzzy weights. That means graph is certain, edges, vertices are certain, but the weights on the edges or weights on the vertices are uncertain. This is another kind of fuzzy graph. And type 5 is fuzzy set with Krebs graph. Certain graphs are there, their fixed graph or Krebs graph are there, but their connection, that means their union or intersection are uncertain. So this is called the fuzzy set of Krebs graph. That means fuzzy set, each element of the fuzzy set are the graphs, and that graphs are the certain graphs are the Krebs graphs. So these are the mainly five basic types of fuzzy graphs, and this is classified by Bloom in the year 2002. After that, lot of variations are available for the fuzzy graph theory. Now I am consider one parameter which is associated with the fuzzy graphs. Okay. And that is nothing but the paths. That one called the paths. Paths are the very simple subgraph, or the you can say that the studied things paths of any graph. For the fuzzy graph, there are interesting things are associated with the paths. So I am defining paths. So what is a path? A path is in a fuzzy graph is a sequence of distinct nodes. Shows that the mu of xi minus 1 xi is strictly greater than 0. What is the meaning of this expression? That means mu of xi minus 1 xi minus 1 xi means an edge. The vertices are considered here x0, x1 up to xn. The consecutive vertices are there here. So the membership value of any edge on the path is strictly greater than 0. So this is the criteria of the fuzzy path. Okay. That means fuzzy path means a sequence of nodes or sequence of vertices shows that each edge has a non-zero membership value. That means it has membership value, some membership value which is not zero. Okay. Now we define the strength of the path. This is the very interesting thing, and this is the studied things. It's the strength of a path. So this is a very simple example of a fuzzy graph, very short, small example of a fuzzy graph. So here x and y are the end vertices of an edge, and a, b, c, d, f are the other vertices. Okay. So the number associated with each edge is written here. So the membership value of the edge XA is zero point 0.3. The membership value of the edge AB is 0.4. BY is 0.6. So these are the number associated with the edges or the membership value. And this represents the nothing but the appearance of the edges in the graph. Okay. Degree of appearance of the edge. Basically, the membership value of an edge means the degree of appearance of that particular edge into the graph. So this is the entire graph. Now, if we consider the path x to a to b to y. So, if you consider the path x to a to c, there is a four different paths from the vertex x to the vertex y. So this is one path x to a to b to y. So we have written here x to a to b to y. And that's what is the strength of this path. So strength of a path means the minimum membership value of the edges. So here the membership value is 0.3, 0.4, 0.6. So minimum is so the strength. That means we say that this edge XA, this edge is the weakest edge of this path. This is the weakest edge. That means if the membership value is low, then that particular edge is the weak. If it is goes to 0, then that particular edge is goes to very weak like that. And if it is goes to 1, if it is 1 exactly 1, then that particular edge is very strong. If it is goes to 1, that means these are not like extremely strong, but these are tends to strong. And if the membership value is near to 0, then that particular edge is a weak. Tends to 0 is weak, tends to 1 is strong. So this concept is used here. So the weakest edge, this is the weakest edge, and its membership value is nothing but the strength. Similarly, another path is there, x to c to y, and its weakest edge is xc, and its membership value is 0.6. So strength of this path is 0.6. Similarly, xy, there is a direct edge between the vertices x and y, and its membership value is 0.2. So strength of this path is 0.2, and the last one, the strength is 0.3. So these are the strength. Means strength means we can literal meaning. Strength means the literally we mention that this is the strength, this is the capacity like that. The same thing is applied here. Strength means. So which path is stronger a path? There are four paths between x to y. So my question is which path is better or which path is strong among these four paths? So we can say that that particular path is strongest path or strong path whose strength is maximum. So see that the maximum strength is here. So this particular this particular path is the strongest path among these four paths. So if you want to go from the vertex x to y, then we have to choose this particular path x to c to y because this path is the strongest path among these four paths. So this is the new concept of the fuzzy graph theory. This concept is not available in our Krebs graph theory, but it is available in the fuzzy graph theory, the strength of the path or the strongest path like that. So the strength of connectedness, the strength of connectedness, that means the strongest path, that degree, the 0.6 is not yet by connectedness. This parameter we have used here, CONNG, between x and y. That means between the two vertices x and y, there are different paths. For that particular example, there are four paths. Among them, the path XCY is the strongest path, and that value, that connectivity, that value is denoted by the con GXY. So this is called the strength of connectedness between the nodes X and Y. So for this previous example, the connectedness between the vertices X and Y is the maximum among the strength between the paths between X and Y, and which is equal to 6. And this is called the strongest XY path. XCY is the strongest XY path. That means XY path means the path between the vertices X and Y. And this is the strongest path. So this is one concept of the fuzzy graph theory. Now, based on this connectedness, we can define different type of arc, different type of paths, which are not available for our conventional graph theory. So these are the new concept, the strong arc and path. So if this condition is satisfied, if this condition is satisfied, this condition mu of xy is greater than equal to connectedness between h minus xy of xy. H minus xy means the graph h after deleting the edge xy. So if the connectedness between the vertices x and y in the deleted subgraph h is greater than equal to mu of xy, then we say that the path xy, sorry, the arc xy is the strong arc in the graph h. Okay. And the path x to y, x0, x1, x2 up to xn, this is called the strong path. If all the arcs are strong of a particular path, then we say that that particular path is a strong path. So similarly we can define different type of strong path based on the relation membership value of the edge and connectedness. See here, an arc xy in G is called alpha strong if mu of xy is strictly greater than connectedness between the vertices x and y. It is called beta strong if it is equal. See that here greater than sign is here equality sign, and here less than sign. So if this condition is satisfied, then we call the arc xy is as a delta. If it is equal, then the arc is beta strong. If it is strictly greater than, then the arc is called the alpha strong. So this is the classification of arcs. Similarly, we can classify depending of the alpha strong arcs. We can classify the paths as alpha strong path, beta strong path, and delta strong arc. That one is not mentioned here. That means if all the arcs of a path are alpha strong, then the path is called the alpha strong path. Similarly, all the arc are beta strong arc of a path, then the corresponding path is called the beta strong path, and similarly the delta strong path. Now I coming into another very interesting topics for the new researcher, the type of fuzzy graph. A lot of variations of fuzzy graphs are now available in the literature. Fuzzy graph. In fuzzy graph, I have mentioning what is fuzzy graph. I have already mentioned that every edge and every vertex has a membership value. Every vertex and every edge has a membership value. If it is a single membership value, then the graph is called the fuzzy graph. Simple fuzzy graph. If there is only one membership value associated with a vertex or associated with an edge, and if there are two things, one is degree of membership value or another is degree of non-membership value, or we can say that the degree of acceptance or degree of rejection. If we consider two things simultaneously for a particular vertex or a particular edge, then that particular graph is called the intuitionistic fuzzy graph. See that in fuzzy graph, there is only one thing, only one parameter is considered. That one is known as degree of membership value or degree of acceptance. But here we consider two parameters, degree of acceptance and degree of non-acceptance, or you can say the degree of rejection. If we consider two things for same parameters, same things, then we can define another type of fuzzy graph called the intuitionistic fuzzy graph. There is another kind of fuzzy graph called the bipolar fuzzy graph. That means in bipolar fuzzy graph, there are two types of membership value. One is called the positive membership value and another is called the negative membership value. For example, if you consider for a suppose there is an election and lot of people are say at the contesting that particular election. So if you pick up a particular person, say X person, that particular person, that particular leader, you can say the political leader has some good activities and that particular person has some negative activities. A particular person has a very um, he did many good works. Also, simultaneously, he did some bad works. Say we may say that that particular people say he has say antisocial. If you consider he is antisocial, so antisocial things is a completely negative one. So how much he is antisocial, that represents the degree of negative membership, and how much he is a good person. That means he is say donating a lot of money to the poor people or donating a lot of money to say in a crisis situation like that. So these are the good things. So if a person, it is generally happen for a particular people, that particular people has some good characteristics as well as some bad characteristics. So good characteristics is represented by positive membership value and bad characteristics are represented by the negative membership value. So this is the another representation. This is called the bipolar fuzzy graph. And picture fuzzy graph is also there. In picture fuzzy graph, there are three things for a same particles or same members. Mu x, member of acceptance, mu x members degree of rejection, and eta x degree of neutrality, neutral values. For example, if we consider the NCR, no? So some people are considered that that particular laws is very much useful for us. So this is the degree of acceptance. Some people are accepted that laws, some people rejected that particular laws, and some people are saying that we have no idea about that particular law. Okay, so X is a law, and that particular law is supported by some people, that means mu X. Some people are rejected that particular law, that means mu X, and some people are saying that we have no idea about that particular laws. So these three parameters can be associated with a single vertex or a single edge. So if these three parameters, if we consider three parameters for a single entries, then that particular graph is called the picture fuzzy graph. And note that the sum of these three things is lies between 0 and 1. So this is another variation of fuzzy graph theory. And if you consider the membership value within an interval, so determination of membership value of an element is a very tough job. So if we consider the membership value as an element, then it is a fuzzy graph theory or fuzzy things. If we consider the membership value as an interval, then we can say that it is an interval value fuzzy graph. That means if each vertex or each edge is associated with a interval number fuzzy membership values taken as interval numbers, then it is a interval value fuzzy graph. Similarly, if we consider this is the membership value, interval value membership. Membership value within an interval. Interval means the lower limit, upper limit are there. And this is the interval. This is the non-membership value. So if we consider the membership value as an interval values, non-membership value as an interval values, that means this is the combination of interval value fuzzy set as well as the intuitionistic fuzzy set. Sorry. And combination of interval value fuzzy set and intuitionistic fuzzy set, we can construct the interval valued intuitionistic fuzzy set. And from this fuzzy set, we can construct or we can define the interval valued intuitionistic fuzzy graph. And there is another variation. Each edge or each vertex is connected with the membership value as well as non-membership value. And if the membership values and non-membership values satisfy this condition, the mu x square plus mu x square is less than or equal to 1, then that particular fuzzy graph is called the Pythagorean fuzzy graph. So this is the variants of the intuitionistic fuzzy graph. In intuitionistic fuzzy graph, there are two numbers, two parameters. One is membership value mu x and another is non-membership value mu x. And sum of the membership and non-membership is taken as less than or equal to 1. But here, sum of square of the membership and non-membership lies between 0 and 1. So this is called the Pythagorean fuzzy graph. So this is the Pythagorean law, most Pythagorean law. So for this situation or for these properties, this particular graph is known as Pythagorean fuzzy graph. And another variations are also available in literature. But this is the highlight. Actually, we have not discussed in details about the fuzzy graph, intuitionistic fuzzy graph, Pythagorean fuzzy graph, interval value fuzzy graph, bipolar fuzzy graph, like that. But these are the variation. I have just spelled out this word for you to habituated with these terms. So these are the lot of theories are there. Pythagorean fuzzy graph is a very big subject today. Intuitionistic fuzzy graph, this is a very big topic. So every particular fuzzy graph is a very big topic. Lot of people are develop or design lot of papers on each of this type of fuzzy graph. Okay. So these are the highlighted terms. These are the variation of the fuzzy graphs I have mentioned here. Another fuzzy graphs are there. Nucleospheric fuzzy graph I have not mentioned here. Recently, Q-Rang orthopair fuzzy graph is also there. And spherical fuzzy graph are also there. So these are the just term I have introduced before you to habituated with it. So anybody if interested to work with fuzzy graph, they can study each of this particular topic. Now I'm define another variation of fuzzy graph, the strong fuzzy graph and complete fuzzy graph. So this is the condition. If this condition is satisfied for all edges, then their particular fuzzy graph is called the strong fuzzy graph. And if this condition mu xy equal to minimum of sigma x sigma y, if this condition, equality condition, is satisfied for all xy belongs to V, and it means this condition is true for every pair of vertices. And here see that the condition is same, but this condition is true for all edges, not every pair of vertices. Here every pair of vertices, and here the condition is true for every edges. So if this condition is satisfied, first condition, the graph is strong fuzzy graph. And then if the second condition is satisfied, then the graph is complete fuzzy graph. So this is a diagram of complete graph, the Krebs complete graph. You see that the complete graph K16, the complete graph is not 8 by K, and the 16 suffix represents the number of vertices. See that in this diagram, there are total number of vertices. Red, this is mentioned here, red in red color. There are 16 vertices, and every vertex is joined with other vertices, other 15 vertices. every vertices are connected with every other vertices. If this condition is satisfied, then the graph is called the complete graph. Okay, so this is the beautiful structure I mentioned here. I am showing you this diagram because this diagram is very nice. Look is very nice. So I am presenting here. See that the inner circle, there are some structural things are there, some triangles are there, some other geometrical shapes are there. So this is an example of complete graph. This is nothing but the complete graph containing 16 vertices. Okay. So if you consider here with this graph, with this complete graph, if we introduce the uncertain thing, if you introduce the membership value with the vertices with edges, then the particular graph will be complete fuzzy graph. So the first one is the example of strong graph, and second one is the example of the complete fuzzy graph. Now I come into another type of fuzzy graph called the complement of a fuzzy graph. Complement of a fuzzy graph, not graphs. So what is the definition of complement in Krebs set? In Krebs graph theory, that means in the both graphs, the original graph and Krebs and the complement graph, in the both the graphs, the set of vertices remains same. Okay. In two graphs, the original graph as well as the complemented graph, the set of vertices remains same. Only the changes are in the set of vertices. In the Krebs sense, conventional sense, if there is an edge between two vertices in the original graph, then in complemented graph, there is no edge between that particular vertices. And if there is no edges between a pair of vertices in the original graph, then there is an edge between the vertices in the complemented graph. So this is the concept of complemented graph in the our conventional graph theory, but in the fuzzy graph theory, the definition is different. Here also in the fuzzy graph, the set of vertices in original graph as well as the complemented graph both are same. See here, the G is a graph, original graph. Its vertex membership value is sigma and its membership value is mu. And the complemented graph is denoted by G bar, sigma bar and mu bar. So where sigma bar equal to sigma, that means the membership value of the vertices. Sigma is the membership value associated with the vertices, and sigma bar is the membership value associated with the vertices in the complemented graph. So in the both graphs, original graph as well as the complemented graph, the membership value of the vertices remains unchanged. Okay. But the membership value of the edges, mu bar uv, equal to is defined by this ways: minimum of this one, minimum symbol, minimum of sigma sigma v minus mu of uv. That means these are the membership value of the vertices, end vertices, minus membership value of the edges of the original graph. So these are the membership value of edges of the original graph. This is the membership value of the edges in the original graph. Okay. So these are the definition to calculate the membership value of the edge in the complemented graph. So using this formula, we can determine the membership value of the edges. In the fuzzy graph theory or in the fuzzy context, the one interesting thing or new thing is to calculate the membership value. The computation of membership value is a challenging thing or the complicated thing in the study of fuzzy mathematics. So that one is completely different. So this is a theorem which is similar to our conventional graph theory. The complement of a fuzzy graph is the original graph. That means the membership value of the edges mu bar equal to mu of u. So this is the simple proof of this theorem, and this theory is also valid for our conventional graph theory. So to illustrate or to explain the complement, we consider this example. This is a graph containing 4 vertices, and these are the membership value of the edges, which is also associated with the edges, and these are the membership value written with the and this is the complement in the Krebs sense. See that there is an edge between the vertices A and B in the original graph. This is the original graph. This is the complemented graph. So there is an edge between A and B. So there is no edge in the complemented graph. And there is no edge between the vertices A and D. So there is an edge between the vertices A and D. Okay, so this is the definition of complement. Means if there is an edge in the original graph, there is no edge in the complement graph. And if there is no edge in the original graph, then there is an edge in the complemented graph. So this is the definition of complement graph in our crate sets. Okay. Now, in fuzzy sense, the concept is different. In fuzzy sense, the complement graph is this one. Okay, all the edges are there. Red edge, blue edge are the original edges. These three edges are the original edges, and red edges are introduced here. Okay, red edges are introduced here with certain membership values. See that the membership value of the vertices are same. Membership value of the vertices of original graph and the complemented graph are same. Only the membership value of the edges are different. See that the membership value of the edge AB is 0.6 in the original graph, but here the membership value of the edge AB in the complemented graph is 0.1. Is calculated using this formula. 0.1. The age is there, but the membership value has been changed. So using this formula, we have calculated the membership value of the all ages. So all the ages are present in the complemented graph. See that the membership value of the SCD is 0. So I have mentioned earlier that if the membership value is 0, then we never consider that particular element into the picture. So we remove that particular edge from this graph, and this is the final complement fuzzy graph of this original graph. So this is the simple concept of the complement of fuzzy graph. So this is the somehow different of our conventional graph theory, but complement of complement. If you find out the complement of this graph, we obtain this graph, the original graph. So this theory or this condition is preserved for fuzzy graph also. Now I think some time is left. Okay. Now we consider another interesting things, the planar graph. You know the planar graph. Planar graph is a very useful structure, mathematical structure for our conventional mathematics, as well as it is used in the computer scientists. The planar graph is used to design or fabricate the printed circuit. The computer people knows that the printed circuit, to fabricate the printed circuit, the planar graph is very much essential to our CD, to fabricate or the construction of the CD, the printed circuit, the concept of the printed circuit, that means as well as the concept of the planar graph is useful. So what is planar graph? A graph is there. So if we draw a particular graph without crossing of any edge, if it is possible, a graph is given, and if that particular graph can be drawn in a plain paper without crossing between two edges, then that particular graph is called the planar graph. Okay. And if it is not possible, then that particular graph is called the non-planar graph. But in fuzzy sense, the planar graph is somehow different actually. Differently defined that particular fuzzy graph. So if you consider some roads, okay. So this is an example. There is a crossing between the roads. This is one road, YZ road, and this is XW road. So see that this road is empty, almost empty. No vehicles are running on the roads. So we can see that this crossing is very simple crossing. There is no dangerous thing to cross this crossing. That means if we consider the mu wx, if mu wx represents the crowdness of the road wx, that means if we consider the membership value as the crowdness represents the membership value, the degree of crowdness represents the membership value of the particular road. So here we consider wx as a road, and mu wx represents the degree of crowdness of the particular road. So for this road, xy road, the mu xy is tends to 0. That means crowd D. Crowd D means such a bhid basically. So it is the crowdless. So we can say that w mu of wx is tends to 0 or it may be as 0. Similarly, the degree of crowdness is of this road is of the road yz is 0. That means mu yz is taken as tends to 0. So for this situation, this crossing is not a serious crossing. So we can say that there is a crossing, but this crossing is not serious crossing. That means no traffic signaling system is required for this kind of junction of the roads. Okay. And if you consider this type of roads, there is also a crossing. This is the one road, Crowdy Road. This one, see that this road is a Crowdy. Lot of vehicles are moving along this road. And this is another road. This is another road, YZ road. And this road is free from any crowd. No vehicles are running towards this roads. Okay. So we can see that the crowd degree of crowdness of the road YZ is tends to 0. But the degree of crowdness of the road WX, that is mu of WX of this road is tends to 1. That means that here we consider the crowdness of the road, and that crowdness is measured by the degree of the crowdiness or membership value of that particular road. So this road is crowded, so its membership value tends to 0, and this road is not crowded, so its membership value tends to 0. So in this case also no important or no such traffic signaling is required for this kind of crossing. This is also a crossing, but no such heavy traffic signaling is required. But for this case, see that both this road is highly crowded, and in this case, a heavy traffic signaling system is required. So in this road, the mu WX is tends to 1, and for this road YZ, the mu YZ is tends to 1. So these are the three examples or three type of crossing we have considered here. And see that in the first case there is no crowdness. So for the first case there is a crossing, but that crossing is very less important. In second picture there is a crossing. One road is crowded, another road is crowdless. So there is a less important crossing. That means traffic signaling is not required. But in the third case, the highly traffic signal is required. A strong traffic signaling is required. This concept we have used in our graph also. So we have considered here or we have defined here one terms considerable value. That means that particular crossing is useful or not. That one is denoted by this mathematical expression. So mu AB represents the membership value of the edge in terms of the graph, and sigma A and sigma B represents the membership value of the n vertices. So using this definition, mu AB by minimum of sigma A sigma B is nothing but defined as IAB. And this term is called the considerable value. That means that crowdness is considerable or not. So in that sense, we have termed this particular parameter considerable value, and that one is denoted by IAB. Okay, if mu AB equal to 0, that means it is a crowd list, then mu AB equal to 0, and that for this case IAB equal to 0. That means the considerable value is 0. That means that particular age is not considerable. That age has no meaning in the graph. Okay. So based on this value, we define some parameters. See that if IAB is greater than or equal to 0.5, then we say that that particular is effective. Otherwise, that particular is no non-effective. Basically, IAB lies between 0 and 1. See that IAB is defined here. That IAB lies between 0 and 1 because for every graph, mu AB is less than or equal to the lower one. So IAB lies between 0 and 1. So if IAB is strictly greater than 0.5, then we say that the age is effective. Otherwise, the age is non-effective. Okay. And based on this effect considerable value, we define the intersection, value of intersection at the point. So P is a point of intersection between the edges. If you consider a graph is given, lot of edges are there, some edges are intersected with other edges, and some edge is not intersect with other edges. Okay. So if you consider a particular edge is intersected with another edge, so the edges here we consider A, B, and C. There are two edges, and these two edges are intersected in the given diagram at the point P. So at that particular point P, the value of intersection is denoted by IP, and it is nothing but the average of the considerable value. That one I have already mentioned in previous slide. So that one is the average of the considerable value. That one is called the value of intersection at the point. So in a particular graph, there are a lot of point of intersection. So based on the point of intersection, we will calculate another parameter. I will tell you in the example, but this is an example of a non-planar graph. See that this is a non-planar graph, but why it is non-planar? There is one intersection between the edges. Okay. There is an intersection between these two edges. See that, and this intersection cannot be removed by any arbitrary vector. It is not possible. That means see that this is a graph containing five vertices, and every vertex is connected with other vertices. So this is a complete graph with five vertices, and this is the lowest or the minimum graph. That means shortest graph. That means the containing minimum number of vertices, which is a non-planar. That means this is an example of graph which contains minimum number of vertices, and it is the non-planar. So this is an example of non-planar graph. See that this graph, is it non-planar? This is very interesting. And this second graph is intersecting or not. So see that there is an edge between X and Y. That edge is drawn in yellow color. This particular edge is drawn in yellow color, and somebody, I think somebody, some person is this line, the XY edge is visible for some person, and it is not visible for some other person. But there is a line between the vertices X and Y. That means there is an edge between the vertices X and Y, and it is visible for some person, and it is not visible for some other person. And some person may say that, yes, there is a light straight line is there. Okay. So I actually basically see that there is a line, there is an edge between X and Y, but it is not invisible, it is not visible. So we can say that this particular graph is a planar graph. If it is not visible, that means this particular edge is not significant for this entire diagram. If a particular edge is not significant or it has a very low significant, then we can say that this particular graph is a planar graph, okay, with certain degree of planarity. So based on this concept, we define one term, degree of planarity. And that one is defined by this expression, by this formula, 1 by 1 plus IP1, IP2, IPZ, where P1, P2, PZ, these are the point of intersection of the edges in the graph. That means the graph is given, the diagram is given, okay, and we identified that P1, P2, PZ, there are Z number of intersections between the edges. For each point of intersection, we have calculated IP1 using the definition mentioned in previous slide. Okay, so using that formula, we have calculated this IP1, IP2, and so on. So after calculating all the IP1, IP2, etc., we calculated the degree of planarity. This term is defined as degree of planarity of the fuzzy graph. So F equal to this. This is the very important parameter. So this F lies between 0 and 1. It is obviously greater than 0 because all these IP1, IP2, IPZ are positive. So all these terms are positive. So it should be greater than 0. And it should be less than 1 also. Okay. It is obvious. The numerator is 1, or denominator is 1 plus something. Some value lies between 0 and 1. So it is lies between 0 and 1. So if F is tends to 0, then its degree of planarity is reduced. And if it is tends to 1, if it is goes to 1, then its degree of planarity will increase. If that degree of planarity increase, and if it is exactly equal to 1, when it will be 1, if IP1 equal to 0, this one 0, this one 0. That means if all the IP1, IP2, IPZ are zeros, then F will be 1, exactly 1. And when it is possible, if IP1 equal to 0, that means there is no point of intersection. If IP2 equal to 0 means there is no point of intersection. That means there is no point of intersection between the edges. Then obviously that particular graph is a planar graph. So for this reason, if f equal to exactly 1, then that particular fuzzy graph is a conventional planar graph. Okay. And if it is less than 1, then we say that this particular graph is a fuzzy planar graph with degree of planarity is f. So this is an example. See that here P1 is a point of intersection between these two edges, and here also P2 is another point of intersection between the edges. Okay. So we can calculate IP1 and IP2, and then finally we can calculate the degree of planarity. So after calculation, we obtain the degree of planarity of this graph equal to 0.4683. 0.4683 less than 0.5, so it is goes to the non-planarity. If the degree of planarity goes to zeros, then it is non-planarity is high. If it goes to 1, then it is degree of non-planarity, that means the planarity is high. That means it goes to the planar graph. So this is the concept. Intersection is there. Even then we can say that that graph is a planar graph, but that things, that planarity has a degree. That means we can say that this is a planar graph with certain degree of planarity. And if it is low, tends to 0, then it is goes to non-planar graph. And if the degree of planarity goes to 1, then we say that it is a tends to the conventional planar graph. So this is the concept of the planarity. Okay, so these are the I have actually mentioned my main topics. And the time also finished. So these are the references, few references. The first one is a book, fuzzy graphs and hypergraphs. That one published in 2000 by Madarson and Meyer. These are the they have published a lot of papers on fuzzy graph theory. These are our books, Modern Trends in Fuzzy Graph Theory, Fuzzy Graphs, and it is published in this year 2020. Myself, my students, and my another student. Okay, so these are our another papers on fuzzy graph, computation graph, like that. So these are the other papers. Thank you for your patience. And if you have any question, then you may ask.
Thank you so much, sir, for such great presentation. In a very short period, the way you discussed the fuzzy graph theory, it has delighted us. The fuzzy graph theory is now a very important research area due to its wide application in many disciplines. Among different types of fuzzy graphs, the concept of fuzzy planar graphs is very interesting, and all the concept is very useful in real life problem. So thank you for considering us in your busy schedule. Now,
Uh,
I sorry, sir.
yes, nothing, no, no, no.
Okay.
You
So
continue.
I request Dr. Mondal sir, please take up the question answer session. Sir?
Thank you, Anusha.
Hmm.
Uh,
Welcome, sir.
Thank you, Pal sir, for a nice presentation and being a part of our 5 days faculty development program. So here is some question from the participant. The first question is like, what is the role of probability theory in graph theory?
There is a branch of graph theory called the uh, probabilistic graph theory is also there. Okay. Probabilistic graph theory, that one very hard or very complicated. Probabilistic graph theory is there. And in that case, the edges or vertices are uncertain. Some probability is there. And also in probabilistic graph theory, the people are consider another type of parameter, that is the expected length of the path, like that. So if we consider the uh, say weight of a particular edge as a probabilistic value, okay, say the distance between say Calcutta to say New Delhi. No, not distance, sorry. The travel time by year. Travel time by year from Calcutta to Delhi. How much time is taken? Say 2 hour 50 minutes, 30 minutes, around 2 hour 30 minutes. No. So 2 hour 30 minutes is not the exact time. it is not the exact time. So what is the probability of reaching after 2 hours 30 minutes from Calcutta to Delhi? Say it is the probability of reaching from Calcutta to Delhi within in a 2 hours 30 minutes is say 0.8. That means we can say that the travel time from Calcutta to New Delhi by flight is 2 hours 30 minutes and its probability is 0.8. So this is the one kind of uncertainty or probabilistic uncertainty, you can see. So this type of parameters or this type of situation is studied in the probabilistic graph theory. Okay. Say travel time or distance or any other things which are uncertain. So distance is generally fixed, no? The train distance from Calcutta to New Delhi, the train distance is fixed because the train line via some cities, the train lines are fixed. Then that along the particular via certain station, the train distance is fixed, road distance is fixed through some certain states or certain cities, but the travel time is always variable. Travel time, but because the travel time depends on the speed of the particular vehicles or the depends on the driver, this confidence about the driving, it depends on the crowdness or depend on the uncertain things happening on the road, sometimes in a at the rail crossing or say rail crossing are off, so the train or bus or bus or stop like that. Some weather is bad, sometimes it's heavy raining during the roads. So depending on the different parameters, so uncertain things are happening in a travel time, if you consider the travel time. So this is a probabilistic graph theory is there. And similarly, if you consider travel time around 2 hours 30 minutes, other than the probability of travel time equal to 2.30 equal to say 0.8. If you consider this kind of event, then it is the probabilistic thing. And if you say the travel time of Delhi, as a Calcutta to Delhi is around 2 hours 30 minutes. So around 2 hours 30 minutes means it is more or less 2 hours 30 minutes. Okay. So it is a fuzzy uncertainty. We consider around 2 or 30 minutes. So this is fuzzy things, and previous one is the probabilistic. So as per my knowledge, the probabilistic graph theory is more complicated than our fuzzy graph theory, because the calculation of probabilities, I think the probability is not a simple subject, no, but the general people. Calculation of probability is a complicated, so the probabilistic graph theory is a complicated subject. So very few works are available on probabilistic graph theory compared to your fuzzy graph theory.
Okay, sir. Okay, sir. So another question is, someone is want to ask some few future direction or future application of fuzzy graph theory as per present day status.
So I have already mentioned in a slide, no, the different type of fuzzy graphs. Okay. Different type of fuzzy graph I have already mentioned. So fuzzy graph, intuitionistic fuzzy graph, bipolar fuzzy graph, Pythagorean fuzzy graph, and I have not mentioned neurosophic fuzzy graph, pure orthopair fuzzy graph. Lot of variations are there. Lot of people are working. Even then, lot of open areas are available. So in that particular slide, I have designed for that purpose only. So future direction of the fuzzy graph. And for application in my book, we have mentioned 10 different applications. 10 different applications which are completely associated with the fuzzy graph theory. Okay. 10 applications are there. So we applied the image processing. The fuzzy graph theory is applied in image processing, network construction. Even if you add some new parameters with the social networks, no, WhatsApp, Facebook, all these social networks, if you are interested to add something, then you may consider that resource also. So in LinkedIn website is there, LinkedIn social networks is there. So in LinkedIn, you may introduce another parameters. Okay, so in the existing social networks, these are the nothing but graph, fuzzy graph. So you may incorporate other parameters. So this is the very useful application of the fuzzy graph theory. And I think it will be a very good applications if you incorporate something on the existing social networks. And if you create any new social network, that one an excellent job, but you may contribute some new parameters, some new measure on the existence uh, or social network. This will be a very good applications, okay, or very good research. And is there any question? Hello, hello. What is wrong?
Then we talk about Shankar sir, hello. Able to hear, sir? Shankar sir, Shankar Prasad Mandal sir, please unmute your mic, sir.
Am I audible now?
Yes, yes.
Yeah, one question is here.
Sir, one question is there, sir. If you comment on how to draw a graph using local and global variables of a program.
Basically, see, I saw that question. So basically, is a completely different area. Graph drawing. Graph drawing is a complete different area of the graph theory. Okay. So actually, I did not work on the graph drawing. So using some program, we can draw any graph. Okay. And it is very interesting that every graph can be drawn using straight line only. If it may be a 100 nodes graph, it may be a 1 crore nodes graph, whatever may be, every graph can be drawn using only straight line. So this is, I have no much idea about the graph drawing, so the people can study. So I can suggest that you learn or you search in Google graph drawing. Graph drawing is a big subject of the graph theory. So you can read how you can draw a graph, okay, using your.
Yes.
I have no idea actually about that area.
Sir, another question is there. Is 3D fuzzy graph is possible?
Yes. 3D graph, fuzzy graph. If you draw a graph in a three-dimensional picture, there is no problem. And this is not a suitable question, appropriate question. Uh, So one answer is there. It may be that particular participant asking that. See that a graph, if a graph is non-planar, okay. If a graph is non-planar, then without crossing, you cannot draw it in a plane paper. But in application point of view, in a circuit design, electronics people knows more than me. If you want to draw a circuit in a plane plate, no circuit is drawn in a plane plate without the crossing the circuits, then there is a subject called the thickness of the graph. That means if some edges we have drawn in a plain paper and some edges cannot be drawn without crossing, then that particular edges can be drawn in another plane paper. Okay. So using different planes, we can draw all the edges of a graph. This is called the graph embedding in different planes. So if you draw a particular graph using minimum number of surface or plane paper, not surface, plane paper, the minimum number of plane papers is called the graph thickness. Okay, thickness of the graph. So this is the another subject you may see or you may think about this, and this is called the not three-dimensional, or you may say it is a three-dimensional picture. So once plain paper is the ground level, then you draw another plain paper, then you draw another plain paper, then you draw another plain paper. That means minimum number of plain papers is called the thickness of the graph, and that kind of non-planar graph can be drawn using three dimension. Okay, without three dimension you cannot draw that particular graph. So this is the cases where we can draw the graph in three dimension. So electronic circuit or electrical circuit, the people using this concept. So this is the graph embedding. It is called the graph embedding into the planes, graph embedding into the surfaces like that. So this is another big topic.
Thank you, sir. And another question is, in fuzzy graph theory, we have to use the degree of belongingness or fuzzy number directly.
Degree of belongingness. Yes, we have used the degree of belongingness. We have used, okay, and also we can use the fuzzy number. Okay, that is actually in my talk I have used just degree of belongingness, or degree of acceptance, degree of presence, like that. But we have not mentioned here about the fuzzy number associated with the fuzzy graph. Okay. Suppose a graph is given, that graph may or may not be a fuzzy graph, it may be a Krebs graph, but if the distances or the weights associated with the vertices, associated with the edges are uncertain, that means the fuzzy number. Fuzzy number means say triangular fuzzy number, interval number, trapezoidal number, say pentagonal number, a lot of different fuzzy numbers are there. If the weights associated with vertices and edges are fuzzy numbers, then that particular graph is called the fuzzy graph. Okay. That also fuzzy graph. Entire structure is Krebs, but the weights are fuzzy. That particular number, triangular fuzzy number, integral number, like that. That one is called the fuzzy graph. And if we consider, say, this minimum spanning tree, shortest path, like that, so using the modified algorithms are there, or some independent algorithms are there to find out the shortest distances, shortest path, or minimum spanning tree, or any other some parameter network flow problem, like that. So all these things are already published. All these things are already studied. We have published one paper where the vertices, edges are triangular fuzzy number and integral number. Okay. So a lot of papers are there. More than say 200 papers have been published on fuzzy shortest path problem, where the distances between the vertices, that means edge weights, are taken as interval number and triangular fuzzy number. So this is another area of your investigation, or another area of your research. If you consider the words as a fuzzy number, and that one I have not mentioned here as due to the shortage of time, but this is another big areas. So I have already mentioned that the algorithmic fuzzy graph, that in this area, very few number of papers are published, or very few number of papers are working. So there is a huge scope to working in this particular area, right, to design the algorithm.
Thank you, sir, once again. Now over to you, Vanusha.
Thank you, Dr. Mondal sir. Now we move on our next lecture session. Our last speaker, Professor Shariful Alam. He is an eminent professor of IIST Shibpur in the Department of Mathematics. His areas of research interest are mathematical biology, ecological modeling, spatial function, multi-criteria decision making in uncertain environment. He has published more than 62 publications in national and international journals. Today his title of speech will Basic Statistical Tools and Techniques Used in Mathematical Modeling. So I request Professor Alam sir kindly deliver his speech. Dr. Alam sir. Sir, please.
Hello, am I audible now?
Yes, sir.
Yes, sir. Yes.
Yeah. Okay. Thank you to the organizers to invite me to give me the opportunity to deliver a lecture. Okay. So I will not take much time, and so I will just give a preliminary tools on statistical tools and techniques, which is needed in our daily life, maybe in research life also. Am I clearly audible, or sir, shall I increase my volume? Hello?
Yes, sir, you are audible. You are audible, sir.
Okay, okay. So, Yeah. So my topics is just basic statistical tools and techniques in mathematical modeling. Just we'll start from beginning. Let me start with the basic kinds of what is the knowledge about distribution. So I think everybody has some knowledge about distribution. So what is the knowledge about distribution? Okay, take this kind of problem. Suppose let we have given 30 chocolates and let there are 6 students or 6 children is there. So we are just identifying, let this is the X first children is identified as 1, 2. Okay, let there are 6 children. And if I want to say, you just give this distribution. So basically, how we can distribute, we can write 6 chocolates here. Okay, sorry, let 5 chocolates here. 5, 5, etc., etc. And there are 6 students, so each student is getting 5 chocolates. But question arises, is it a smart way to write down the distribution? Suppose I change this figure, in case of 30, I have given 60. So we have to change this table. In that case, if it is all are equal distribution, you have to just write down 10, 10, 10, etc. So here, actually, we assume equal kind of distribution. But in real life, this distribution may not be equal. Okay, it can be user specified distribution. So what is a kind of, okay, what is a smart way to write down any kind of distribution? Basically, we have to identify a random variable X and we have to give a weightage. So let these are the values of X, etc., etc. Let there are n several cases, let there are n students. And suppose we are just giving the equal weightage. So in that case, we can write what is the weightage? Weightage is nothing but 1 by n, etc., etc., 1 by n. Rather than this absolute figure, it is better to write down this probability. So this is the common idea of distribution. Now, this is a standard distribution. By default, it is equal distribution, but it can be user kind of distribution. So let's observe other kinds, some popular kinds of distribution. For example, suppose uniform distribution. Let X can take value 1 to n, and this probability of X is nothing but this is the weightage or probability. Okay. It can be, so in a particular example, it can be let X, it is only taking the value 1, 2, 3 up to 5, and these are the corresponding weightages. And we know if it is a distribution, one property must satisfy the sum of all this probability must be 1. There are other specified kind. So in this way, there can be infinitely many distribution we can describe for a random variable. But there are some standard distributions. Okay. For example, binomial distribution, Poisson distribution. Let me describe the fundamental concept how this binomial distribution is coming in our real life problem. Maybe maximum of your student is habituated to this kind of problem, but let me describe how this binomial distribution is coming. Let's consider this kind of scenario. Suppose there is a shopping mall. Let n customer or let 100 customer visited today, in particular today, 100 customer visited. And let on an average 10% customer buys the product. So if a customer buys the product, then we'll call this thing as a success or successful customer. Let X denotes the number of successful customer among these 100 customers today. Now question arises, what is the value of X? Can anybody tell me what is the value of X? Please unmute yourself and give the answer. Can anybody tell me what is the value of X, or what will be the value of X? Is the question clear? Suppose 100 customer visited, on an average 10% people buys the product, and let X denotes the number of successful customers today. So what will be the value of X? What is the value of X? Anyone? Okay. So actually the values of X, it can take from the values of X can take from 0, it can be 0, it can be 1, it can be 2, it can be 100 even. What is the meaning of X is equal to 0? X is equal to 0 is no successful customer. Okay, 10% is successful. That does not mean this success happens today itself. This is on an average 10% successful. Okay, so it can be 1. 1 means it can happen in that particular day. Only one customer is successful. Even it can be 90 also. Okay. In any case, it may happen that 90 successful customer has happened in that particular day. Obviously, this probability of X for no customer will be successful may not equal to the probability of X. So in this case, probability of X is equal to 0 and probability of X is equal to 10 may not be equal. The success chance of these and these may not be equal, but it will follow some specified rule. So can we calculate how to calculate probability of X is equal to 0? So what is the meaning of distribution? Meaning of distribution means you have to identify the values of random variable. So here the possible values of X is equal to 0, 1, 2, up to 100. Now what is the meaning of X is equal to 0? X is equal to 0. We want to calculate probability of X is equal to 0. X is equal to 0 means all these customers are failure. So that we can visualize as failure, first customer failure, intersection, second customer failure. All these customers are failure. So in that case, and we assume all these customers are independent. And if you just apply these basic probability laws, you will get this is probability of failure, etc., etc. This is probability of failure. And let probability of success is P. Okay, in that case, P is 10%, 0.1, or it can be in general, this is P. And let instead of 100 customer, we are taking a general case, let n customer visited, P is the success chance. And sometimes we get Q is nothing but failure. So this is 1 minus P. So this is nothing but Q into Q into Q. So basically this is Q to the power n. Similarly, if we want to calculate X is equal to 1, basically exactly one success and all are failure. Now this success can happen among these n places, just exactly n one places. So in that case, it will be NC1 and exactly one P also are Q. So this formula will be NC1 Q to the power n minus 1 into P. Similarly, for X is equal to 2, etc., everybody knows this basic calculation. And so in that case, we'll get this kind of distribution. So this is a binomial distribution, means we have to identify the values of X along with this weightage. And weightage, instead of using this table, we can write down this formula. This is that formula. In that formula, if we put R is equal to 0, we'll get this table value. If we put R is equal to 2, we'll get this 1, I'll get this table value, etc., etc. So basically, distribution means we have to identify this kind of table where the possible values of X you have to identify along with the weightage. Similarly, Poisson distribution, this is the distribution, and we can identify this thing. Now, a big question arises. So what is the meaning of meaning of distribution in our real life? Basically, we have to identify the values along with the weightage. That's the idea of distribution, and that idea we dealt in our real life. Now, in case of continuous case, suppose x is a random variable which is taking the value in between 0 and 1. Let x is a random variable which is taking in between the value in between 0 and 1. So let x is a random variable whose value is taking, x is taking any value in between 0 and 1. Question, so how many values, possible values of x are there? First of all, these possible values are infinitely many. The next question arises, is it countable? Obviously, we know these values are not countable. So if it is not countable, we cannot write down these values as x1, x2, etc., etc. This is the first question. So how to represent this distribution is in a tabular form? We cannot write down in a tabular form. And even forcefully, if you want to write down in tabular form, let this is x1 and let all are equal weightage. So what will be that weightage of any particular point? One favorable point, and there are infinitely many points. So this probability will be, so these are the values of x, and this is the probability of x will be 0, 0, 0 everywhere. So writing this kind of distribution in this tabular form will be meaningless. So if x is a continuous random variable, that means all possible values of x are uncountable set. That means x is a continuous random variable. We cannot indicate the distribution in this way. So what is the way out? Okay. So in this case, we forced to modified our concept of distribution. In that case, take a real life example, how generally we describe this distribution. We have enlightened a centered stick here. We enlightened a centered stick here. Okay. A centered stick is burning here and here, so on and so on. So what will happen? Gradually, this obviously centered molecule will diffused, and this after diffusion, this centered molecule will goes in this side up to infinity, and this side up to minus infinity. But the amount of scent everywhere will not be equal. The amount of scent everywhere will not be equal. So question arises, how we can describe the amount of scent? So the distribution of amount of scent or scented molecules are not equal. So how will indicate? So we applied a kind of concept. So what is the density of scented molecule around here? Let this is a particular point x. Let this is a particular point x. We take a small strip of length dx. So within this strip area, how much scented molecules are there? If the scented molecules, basically that weightage within this area, that is nothing but concept of density. If it is within unit volume, what is that mass? That is nothing but density. So we are indicating the density around this point. If this density is high, so if this is a scented stick here, what will happen? Obviously, we know from our practical life example or experience, the amount of scent around this scented stick will be higher. And if we move gradually from this point, obviously amount of scent will decrease. And in that case, density curve can be indicated just like this kind of curve. And this indicates the density, amount of scented molecule within a small thin area. That is nothing but density. And this amount of density indicating through this curve, so this is called density curve. So in case of continuous random variable, to describe the distribution, we need this kind of density curve. So take one, we know some standard kind of distribution, for example, uniform distribution. What is the meaning of uniform distribution? Suppose in this room, I enlightened a center district, okay, or I spray some I spray some scented spray has been done. We wait for another 2 hours so that it's reached to the homogeneous condition. So in that case, the amount of scented molecules everywhere in the room will be same. That means density everywhere will be same. Don't consider in 3D space, just we are considering let within the length AB, that within the length of this room AB. Let here the amount of scent is same, here at that point is same. So what will be the density curve here? It will be just parallel to x-axis. And outside this room, that means outside this range AB, this curve will be, value will be 0. So in that case, the density function can be easily written as, okay, some constant, if it is the value is within a to B, otherwise it is 0. And what will be that height of this, that value of this constant? From basic calculation we can show, since total area under this curve is nothing but total probability. From there we can calculate the value of k is nothing but 1 by b minus 1, because if this height is k, the value of k will be, and that k into a minus b, that product will be 1. So obviously k will be this thing. Now, in case of scented molecule, if I just enlightened a scented molecule in a room, and if we observe the density, this density can be represented through this kind of curve. And basically this is a called normal distribution. And its mathematical form, easily we can write this mathematical form, but derivation there are lots of ways. For example, how the scented molecules is diffusing, just following the Brownio's law of motion. If we just apply the physical or mathematical form of the Brownio laws of motion, you will get this equation of this curve, or sorry, not equation, this functional form of this curve can be represented in this way. And we know this here mu is nothing but this position of the scented molecule, the center district, and that is nothing but mu, and sigma is that nothing but standard deviation. What is the standard deviation? We will discuss little bit later on. Okay. So this is the kind of distribution. Up to this thing, any question? These are the preliminary kinds of thing. Is there any question till now? Please raise your question. If there is a question, I want to give the answer, then we'll move forward. Up to this is the basic idea about statistics, any kind of distribution or continuous distribution. Is there any confusion till now?
No questions are still. Please,
Okay.
sir, continue.
Okay, so you see, now there is this basic normal distribution curves follow very good, very interesting property with respect to its area property. So what is that area property? And there is another important concept is associated, is called Six Sigma concept. So any kind of normal distribution curve, it is observed, whatever is the value of mu, there is one sigma level, 2 sigma level, 3 sigma level. What is 1 sigma level? Basically, before this thing, let me clear what we are trying to do with any kind of statistical data. Okay, before describing this kind of concept, quickly go through a review. So basically, in a statistical problem, take a statistics. Suppose your job, you have to predict what is the average production, agriculture production in a particular district. Okay, so suppose in this statistical calculation you are trying to perform, what will be the total or forecasted production in a particular district of wheat production. So how will predict this thing? So for this thing, you have to collect the data. Now, there is lots of issues in the collection of data. First of all, how to collect this data? There are lots of techniques. So basically, in this case, you have to collect this data. Suppose this whole sample is there within the district, lots of plots are there. So this is the total sample. This is the total sample. Now, from this, actually this is called population. Total population. From that population, obviously will not access the whole population. We'll take a subset of this data. So from the district, we'll take some sample value. What will be that optimal sample, etc. That's the issue, and that is called sampling issue. Suppose we picked up 1,000 some samples from different area, and what will be this? There are lots of sampling technique. What will be your what will be the accuracy of your prediction? That crucially depends on this sampling technique. Okay, and there are lots of sampling techniques is there. Suppose using a appropriate sampling technique, we choose a sample data. This is that sample data. So in that sample data, there are 1,000 data are there. So within this data, what we will do? First, we have to calculate the location parameter. So what is that location? First, we have to calculate maybe this data has some kind of distribution. It may follow normal distribution, or it may follow other kind of distribution. So if it follows let's assume it's following normal distribution or any particular kind of distribution. It may follow some discrete distribution, it may follow some continuous distribution. So first you have to predict any kind of prediction. First you have to predict a parameter value. Around that parameter value, we have to predict this. This is the expected production in this coming year, etc., or whatever this kind of thing. So in that case, first in that case, first we have to calculate that mean. And what is the definition of mean? Everybody knows. Basically this mean is nothing but expected value of x is nothing but summation of xi into pi. In our childhood, actually we defined what is the mean of, suppose let x1, x2, let 5 values is given. So what is that mean of this 5 value? Let x1 plus x2 plus ... plus x5 by 5. Basically this is nothing but x1 into 1 by 5 plus x2 into 1 by 5 plus etc plus x5 into 1 by 5. This is that mean. So in case of, say, if it is a equal distribution, basically what is that same mean? In case of, but in our childhood we assume this is only equal distribution. If it is not equal distribution, this summation will be xi into pi. Pi is nothing but corresponding probability. This probability may not be equal. For example, in case of binomial, these probabilities are not equal. Now, in case of continuous, this summation will be replaced by integration. These values xi, I cannot write down as a, since it is an uncountable kind of variable. So since it is a continuous random variable, the values of x are uncountable. We cannot represent as xi. So we are representing as a x. And this probability is nothing but area under this curve. This is the mass. So its height is fx, and its small length is dx. So within this thing, what is that mass available? This is nothing but probability. So probability is fx into dx. So this is that formula. Now this is actually called first moment. Similarly, we can define the rth raw moment. And why it is raw? Raw means directly we are using this value. Okay, what is the meaning of raw? Suppose in case of hard drinks, raw means we are basically without mixing up any kind of water, etc. That's the raw drinking. So directly we are using this value. No kind of modification is there. And this is rth raw moment, means we are just putting rth power. And in case of continuous, this is this thing. Similarly, rth moment about that point A. So basically we will dilute these values, we'll modify this value, and we'll calculate this thing. So first we'll calculate the mean of this data. So what is the mean of whatever this data we have collected? First we have to calculate the mean of this thing. So this is that location parameter. Suppose our mean comes, let 200 metric ton wheat production of that district. Now question arises, if I say my production or next year this production figure is 200 metric ton, what is the chance or probability that my prediction will be correct? Because this production can take any value in between, it's a continuous random variable. Since you are predicting a point prediction, obviously a point prediction, that correctness will be almost zero. So obviously this kind of prediction is meaningless. So what is a good prediction? We have to predict within an interval in a state of a point prediction. Suppose I want to predict, okay, suppose I got that mean is equal to 200 metric ton. Instead of predicting 200, if I around this 200 metric ton, if I choose a range, let it is from 195 to 204, within this range. Okay, if you want to predict, obviously there is a greater chance that my prediction will be correct. So my job is I have to predict within a interval with high accuracy. Suppose one says no, what is suppose mean is 200. One predicted, okay, what will be your prediction? This prediction will be 0 to 10,000 metric ton. Obviously it will happen. So if you give an absurd kind of range, obviously it will happen. So what is my crucial issue? My crucial issue will predict within a small interval with high accuracy. Now for this kind of prediction, first thing we need is the location parameter or mean. Now this mean is not only one thing for that prediction. You need another kind of moments. For example, you need standard deviation or variance for this prediction. Just little bit go through it. Suppose we have a data set here. This is the first data set A. And let whatever this data you have collected, just like this, these are the 1,000 data you have collected. Okay, and let second team, they have collected this kind of B kind of data set. And third team, they have collected this kind of data set. So obviously question is, if I use this kind of data set A and data set B, which kind of data set will give the better prediction? Obviously data set A will give the better prediction because here fluctuation is less. But in between B and C, which data set we can choose? In between B and C, the choice is not obvious. Okay. Basically, this kind of problem we can visualize. Suppose let in one place, let there are 20 kgs of potato, and another place let there are 50 kgs of potato. Just looking this amount, we can distinguish that there is the much amount of potato is there. Here the less amount of potato is there. So from eye inspection, it is clear. Here the fluctuation is less and here the fluctuation is much. So if I use this data set, obviously my prediction will be not good. But if these two scenarios, let's scenario B and scenario C, in that case, which kind of data set will choose? So basically, let there are in one place let there are 50 kg potato and another place let there are 49 kgs potato. So to choose which option is better, we need a measurement tool. So similarly, here we need a measurement tool. So what is that amount of fluctuation? to measure the amount of fluctuation, we know we can use separate kind of tool, but all these tools are not good. If I use just error function or mod function, this will not work. And obviously, this variance, that kind of function will work. And we know what are the difficulties of the use of this kind of function and what is the advantage of this kind of function. We are not discussing here. Obviously, this is the second central moment we are using to measure the variance. And is a square root is called standard deviation. So now, along with this location parameter, we will took another parameter. This is variance or sigma square. So sigma is nothing but square root of this variance, or it is called a standard deviation. Now, with this help of this thing, how to predict, or what is that confidence interval which we will try to predict? Okay, let's come to this point. So a normal distribution satisfies a beautiful property regarding its area property. What is that area property? This is 1 sigma level. So whatever this mean of a standard normal distribution within this 1 sigma level, that means 1 sigma level means from mu minus 1 sigma to mu plus 1 sigma, within this area, within this range, the area is fixed, and this area is 68.27%. Similarly, if we move from mu minus 2 sigma to mu plus 2 sigma, this area is fixed. This is called 2 sigma level, and that area is 95.45%. And what is 3 sigma level? 3 sigma level is nothing but from that mean, if we move towards left hand side up to 3 sigma, and from right hand side up to 3 sigma, that means this range will be mu minus 3 sigma to mu plus 3 sigma, and within this range, this chance of or any data will be within this range, that chance is 99.73%. Okay, it will be clear if I give you one example. For example, let in a particular case, let mean is equal to 50 and sigma is equal to 10. So what will be that 1 sigma level? So from that mean, mu, you move towards left, distance 10, and from mean mu, from right you move 10 distance. So that range will be 40 to 60. That means probability any data within this range from 40 to 60, that chance is 68.27%. So that probability, in terms of probability, we can write down that 68.27% can be written as 0.6827. Similarly, what is 2 sigma level? This will be from 30 to 70. That means mean is equal to 50. From here, you just move 2 sigma in left hand side, it will be 30. From here, 50 is the mean. You move this side 2 sigma distance, sigma is 10, so 2 sigma is 20. That means you have to move in right from 50 plus 20, that means 70. So within this range, that chance is 95.45%. Okay, and 3 sigma level, what is the 3 sigma level here? It will be obviously 20 to 80, and that chance is 97 point, sorry, 9, this is a printing mistake. This is 99.73%. This will be 99.73%. Take an example, then it will be clear. Suppose the yield of rice in a plot of 1 acre plot follows normal distribution with mean 60 kg and standard deviation 50 kgs. Let you have cultivated rice in a plot of 1 acre. How much you are confident the production of rice in your plot will exceed 700 kgs? So in that case, this mean is equal to 600 here. This is the 600. So basically 1 sigma means if you move 1 sigma, this is 650, and 2 sigma is nothing but 700. So up to this thing, what is that probability it will cover? So if probability of x greater than is equal to 700, that means only this area, only this area, this area and this area. And what is that chance? This 2.17% plus 0.17%. So that chance is this thing. So how much confident? Only you are confident that what is the chance? 2.27% chance this production of rice in that particular plot will exceed 700 kgs. Okay, now this kind of prediction you can apply everywhere. For example, suppose this is a big kind of public exam. This is a GATE exam. Okay, let the score follows normal distribution. Okay, with this kind of feature, let mean is equal to 50 and sigma is equal to 10. Suppose a student gives the answer or his score is more than 80. He is expecting more than 80. So easily he can calculate what will be its rank. Because what is the probability that probability of x greater than is equal to 80? That chance easily you can calculate not only 80, if it is 82 or 83. From this probability curve, we can calculate maybe only 1%, 2% student will beat him. So if it is like total applicant or total number of candidate appears in the exam is 3 lakh, easily he can calculate how many students will be, or easily he can calculate its rank using this kind of method. Now another concept is Six Sigma concept. So what is Six Sigma? Since normal distribution will never truncate, it will goes on and on, because suppose the centered molecule is diffusing, it will be diffused from minus infinity to plus infinity. It will goes on and on. So we already noticed one thing. Within 1 sigma level, it is covering 68.67%. 2 sigma level, it is covering 95.45%. Within 3 sigma level, it is covering, this is not 97, it will be 99. Here, this is the correct figure, 99.73%. So obviously, if it is 4 sigma level, that will be more than this thing, more than 99 point something, but it will never touch 100%. If it is 100%, because beyond this thing, this curve will not exist, truncated. So this is not that case. So obviously, so 4 sigma level will capture more chances. 5 sigma level is nothing but from mu. If we just move 5 sigma distance from right and 5 sigma distance in left. Similarly, 6 sigma is nothing but from mean. If we move 6 sigma in right and 6 sigma in left. So basically, 6 sigma level indicates, that's a very crucial level, it indicates 3.4 defects per million opportunities. Basically, we are assuming the area under this curve is 1 million. So basically, in 6 sigma level, how much area it will be covered? It will be covered maximum areas. Better to say how much area will be left. So in 6 sigma level, we can say, if it is a 6, okay, within the 6 sigma level, if we assume this is a normal distribution, this is the mean, and this is the 6 sigma distance. Let this is mu plus 6 sigma, and this is the mu minus 6 sigma. So maximum data will be covered within this area. If area under this curve instead of 1, if I just assume it is a 10 to the power 6, that means 1 million. Better to say how much area will be left beyond this 6 sigma level. That area is only 3.4. That means this area is 10 to the power 6 minus 3.4. Okay, and this property is true for all values of mu and sigma. That does not depend on mu and sigma. In your problem, suppose if mean is 100 and sigma is 5, you can apply this property. So this property always holds, and that does not depends on the particular value of mu and sigma. That's the beautiful area property in case of normal distribution. Now, you see, in industry, probably you are habituated with this kind of term, Six Sigma concept. Industry, we are using this concept. What is Six Sigma company? Suppose a company is producing bulb. He can claim himself as a Six Sigma company if within 1 million, the number of batch production, if it is less than 3.4, then he achieved this level. This is a service company. So within giving a 1 million service, if your batch service is less than 3.4, obviously you can tag a Six Sigma level with your company. So basically, this is a very crucial kind of level. If any company achieves Six Sigma level, he can go for the target of 8 Sigma, etc. Not only this thing, Six Sigma concept can be attached everywhere. For example, you can attach as a Six Sigma student. How we can attach this kind of concept? For example, let a student appear in 1 million exam. If number of unsuccessful exams is less than 3.4, then he will be declared as a Six Sigma student. Similarly, as a teacher, you can attach yourself as a Six Sigma teacher. So if you just discuss about 1 million problem, and if it is unsolved problem is less than this thing, you can attach in that way. This is that Sigma. That means Six Sigma concept can be attached as a managerial decision everywhere. And originally it is coming from this sigma of this normal distribution. Okay. Now come to this thing, modeling kind of portion. Suppose we collected some data, and from that data, a particular parameter is measured. Now, whether that parameter is significant or we are getting a model output. Suppose from a model we get a kind of output. It is a optimization model, and in that optimization model, let's say we are inventory management model, and we are getting a cost. From another model, we are getting another kind of cost. So, question arise? Is there any significantly difference between these outputs? So we have to compare this kind of thing. So you have to make a kind of judgment. So one thing you can do, that is a kind of prediction problem. Another kind of thing you can do, this is nothing but a judgment kind of problem. Any statistical kind of problem, mainly we can categorize in two categories. Either it is a prediction kind of problem, or it is a judgment kind of problem. So this judgment kind of problem, basically this is nothing but testing of hypothesis. So I'll just enlighten few things on this judgment kind of problem. Suppose, okay, let me consider one real life problem. Okay, suppose there are two companies, company X and company Y. Both are producing sleeping pill. Somehow, now let company A claims that their medicine is much better than the company B. And the reverse claim is done by the company B. That means he is claiming that his medicine is better. Now question is how to justify about their claim. Who is better, or is there any difference between this thing or not? In that case, to justify this kind of problem, so first we have to make a hypothesis. So what is a hypothesis? Hypothesis is nothing but a kind of a statement. So what kind of a statement we can frame here? Obviously we can frame, no, there is no difference between them. This is one kind of a statement. What is the alternative statement of this thing? Yes, there is the difference in performance about the sleeping pill of these two companies. This is the alternative hypothesis. Okay. Or it may happen any kind. This kind of hypothesis can be done in court case also. Suppose police has produced one man and he produced this thing as a theft. In the judgment system, you have to declare, or you have to you have to make a judgment whether he is a theft or not. If he is not theft, you have to release him. If it is a theft, you have to give the punishment. So in that case, in the judgment system, you have to decide there is a null hypothesis. What will be the null hypothesis kind of a statement? And what is the alternative hypothesis? Just negative of that statement. Now there is a principle to how to construct the null hypothesis. First of all, this construction of hypothesis is very important. Okay, in that construction of hypothesis, generally there will be a null hypothesis and there is an alternative hypothesis. Okay, but you have to remember one thing: whenever we write anything in this null hypothesis, there must be unbiasedness in that kind of statement. What is that unbiasedness and why we are assuming unbiasedness in null hypothesis? It will be clear just within few minutes. Suppose in a you are the third umpire. That means you have to judge whether Saurav Ganguly was out in a particular match or not. So in that case, null hypothesis will assume she is not out. Okay, he is not out. This match, Saurav Ganguly is not out. Or in case of, suppose a man has been produced by a police in the court and they claim that he is a thief. In the judgment, judge will assume that man is not a thief. Whenever, because there is a human being, nothing has been tagged with him. So what will be the null hypothesis? No biasness should be there. Okay. For example, in first part, he is a player. Okay, why you will give him out? Obviously, he will play. So null hypothesis is not out. Okay, in this case, in the judgment system, in case of theft, null hypothesis is not a theft. What is the alternative of this thing? Alternative is just opposite of this thing. So in this case, alternative will be out and this thing. Now you see, what will be this judgment system now? Judgment system, suppose this is the true state. H0 is true. What is H0? That means actually the Ganguly was out. Okay, and this is your judgment system. In the it may happen H0 is true, or it may happen H0 is false. Whether true or false, only Ganguly knows. Or very close to him, or suppose in this case, a man was produced in that court. In that case, whether he is theft or not, only he knows and God knows. Okay, whether he is a theft or he is not a theft. Now, according to the judgment system, judge is giving some opinion. This is the either reject H0. Reject H0 means, in this case, will reject H0 and accept H0. Only these two decisions can be happening. Now, suppose this true state is H0 is true. Somehow judge give this kind of decision, reject H0. So what is happening? So in the results, some wrong, obviously some error or wrong is happening in this decision. Some error is happening. Basically, what is the scenario here? Actually, he is not a theft, or Ganguly is not out, but somehow the decision comes, it is out. This is an unfortunate decision. So there is error, and this is called type 1 error. And what is this case? Actually, H0 is true. That means this man is not a theft, and accept H0. So judgment system, they give the same kind of judgment. So this is the correct result. And this thing H0 is false. Basically, this man was a theft, and reject H0. That means judgment has accepted that decision. This is correct. But suppose H0 is false. That means he is a theft, but accept H0. So the judgment is given as no, he is not a theft. So again, there is an error. But among these two errors, obviously, type 1 error is much serious. Okay. In this error, what is happening? Actually, this human being was not a theft, but due to this judgment system, he is declared as a theft. So obviously, this is a very serious error. And obviously, in type 2 error, this is also error. But we should be careful that this type 1 error should not be exceed much. Generally in 1% level, that means within 100 cases, I can allow only one case this kind of error. So actually in judgment system, what we are doing, basically that judgment system is very simple, sort of the sample observation. So we make a partition. Let if this observation comes here, so this is the whole sample space. We are making a partition. So if some observation comes here, we'll reject H0, and if it is comes here, we'll accept H0. So decision is very clear. Either reject or accept. This decision is very clear. So actually, those kind of observation for this judgment goes here, rejecting H0. This is called critical region. Critical in this sense, suppose a patient is critical. Basically, we cannot save him. Basically, judge is always in favor of this H0 because in H0 there is no biasness is there. So judge want to take the decision that I will not reject H0. But if suppose in a judgment system, a man has been produced in the court within let 100 evidence, 98 evidence goes against him, only 2 evidence in favor of him. In that case, just forced to accept, forced to reject H0. That means he will declare this thing as a theft. So basically, this is that whole decision is can be just partition in any sample space. If it is comes here, we'll reject this thing. It is comes here, we'll accept this thing. This is that simple decision. And how to make this decision? There are some theories involved here. We'll apply this theory. This is the simply this criteria is there. Neyman Pearson's criteria is there. So according to this thing, we can decide it that some mathematical calculation is involved to decide this critical region. So simply, if it is false there, we'll reject this thing, we'll accept this thing. This is that mechanism. So according to this mechanism, which we can do it. So you come to this thing. Suppose, come to this problem. How will take this kind of judgment system? Suppose there are two companies, A and B. This kind of controversy arise. You have to follow. So we frame the hypothesis. This is the null hypothesis. This is the alternative hypothesis. In null hypothesis, we assume there is no difference among the performance between these two. In alternative, we assume there is a difference between their performance. Okay. Now, in second step, we have to collect the data. Let this is the data we collected. N number of data. Let 1,000 data we have collected. So this is the paired data. So we collected the data for the medicine, administrative for the company A, and collected the corresponding data. So what is the sleeping time? Let after taking that pill, let it takes 5 hours time for the average sleeping. And in case of same kind of medicine, same dose for company B, we have administered. And what is the average kind of sleeping time? Let's say sleeping time is 4.5, etc. Okay, we collected this kind of paired data for large number of cases. Let Zi is a random variable is difference between these two data. So obviously now standardize this Z variable. If it is a standardized this thing, let Zi is follow obviously normal distribution. Okay, if there is no under null hypothesis, if there is no difference, what will happen? Basically, there will be no difference between their performance. So their performance will be very close to 0. Now, instead of 0, it can be let 1, it can be minus 0.5, it can be -1. But if this observation comes like let 3.5, very unlikely, because under this observation, if Z observed calculated as, it will be very close to 0. If under this null hypothesis is 0. If there is no difference, obviously this Z observed value will be, if there is no difference on an average, that value of Z will be very close to 0. So if value Z observed comes, For example, 1.2. Yeah, it may come. There is no significantly different. But if Z observe comes, but like this, 3.5, very unlikely, because under this assumption, since sigma here sigma is equal to 1, since we standardize. So what is the 3 sigma level? 3 sigma level means from 0 to it can be up to 3, here up to -3. So it is beyond 3 sigma level. That means it is exceeding this 0.9973% that level also. So obviously we have to reject it. That means there is a strong evidence, yes, no, there is a difference between their performance. Now, if it is, let Z observe is 1.2, 1.2 means it will fall somewhere here. Obviously, there is no strong evidence against the null hypothesis. We cannot reject. I generally will reject if I get a strong evidence against him. A strong evidence means obviously Z observe will be very far from 0. That means there is a strong evidence. Now you see, so in first two cases, this is the extreme case. We'll reject. Here, there is no question of rejection. But this kind of case, let Z observe is 1.9 or 1.97. That means in 95, around 95% level. So whether we'll accept or not, or reject, whether we'll accept or reject. In that case, suppose I accept this thing. Is there any valid reason to reject this thing? Generally, in our test, we perform in a fixed level, 5% level or 1% level. In 5% level, if it is beyond 95%, we will reject. And within 95% level, we will accept. But if I consider this thing in 1% level, basically 99% level, we will accept. Beyond 99%, we will reject. But this is a generally kind of fixed kind of concept. We want to make a dynamical kind of scenario. In that case, we'll just calculate. Suppose Z observe is comes here. So after that thing, what is the probability is occurring after that point? That probability value is called p value. Now, if Z observe comes towards a very extreme point, obviously p value will be less. P value will be less, so high chance of rejection. But if p value, suppose Z observe comes here, obviously p value will be high, so there is a less chance of rejection. Okay, so this is the kind of principle we'll adapt to accept this kind of judgment principle. So obviously in modeling kind of performance, we can adapt this kind of test. Not only this is called actually Z test. Similarly, if this underlying distribution is a T distribution, then we can adapt this kind of principle and we can take a decision. This will be called T test. Similarly, Z test is not for mean level, generally for variance level. Is there a difference between the variance between two distributions? Generally Z distribution, but this is the basic principle we'll apply in case of judgment system. That's all. I think that I already took more than 1 hour time. So is there any question?
Yes, sir.
Thank you, sir. Thank you so much for such a great talk. In a very short period of time, the way you discussed the topic, it has delighted us. You discussed that in mathematical modeling, many benefits and many beliefs and real-life problems are translated into the precise language of mathematics. So thank you. And also you discussed some basic statistical tools so that any participants can understand this topic easily. Now, let us take some question answer session. So I request Dr. Model sir to please take up the session. Sir, please.
Thank you, Anusha, and thank you, Dr. Shariful sir, for giving nice presentation and being a part of our 5 days faculty development program. Sir, here is a question.
Yeah, what is the question?
Yes, sir, I am read it.
Yeah.
That a participant asks how this percentage level coming 1 sigma 68%, 2 sigma 95.45%, 3 sigma 99.73% is coming?
Yeah, that's a good question. Actually, you see, that area under this curve can be calculated. So basically, from mean. So yeah, say for example, let this is a sorry. Okay, let this is that mean. So mean is equal to let.
Sir, screen is not visible, sir.
Oh, so I think
share screen. You have to come for share screen.
yeah. Just 1 minute. I think share screen option is here, no?
Yes, sir. At the bottom there is a green icon.
This screen is okay.
Green.
Share.
Green.
Yeah. Is it visible now?
Yes, sir.
Yeah. So you see, this fx function is given as a 1 divided by root over 2 pi sigma e to the power minus x minus mu, that whole square by 2 sigma square. Okay. Now question arises, what is the probability of, let within 1 sigma level means x minus mu less than is equal to x less than is equal to x. Sorry, this is mu minus sigma. Sorry. So this is nothing but, so this is probability of mu minus sigma less than is equal to x less than is equal to mu plus sigma. So basically we can integrate this thing within this range mu minus sigma to mu plus sigma, f of x area under this curve, let this is that, this thing, let is mu minus sigma, and this is mu plus sigma. So now we can put this function. Now this performing this integration is a really challenging job. Actually, we perform this integration using a software, and this corresponding table is made. This is called normal distribution table. So from that normal distribution table, we can calculate that value. Otherwise, performing this integration, you can calculate that value. Is it clear? So if
Yes,
you perform this integration putting this function, obviously you have to perform this integration by numerical integration.
Yes.
That approximate value is 60 in 1 sigma level for any kind of normal distribution. That value is always 68.67%. Any other question?
Another question is, sir, if p value is equal to 0.05, then null hypothesis is?
No, actually, I want to put p-value determines whether we will accept the null hypothesis or not. Okay, so p-value is in the finalist, in the first step of any problem. You have to decide the null hypothesis H0. What is that null hypothesis? Generally, let mu A is equal to mu B. In case of medicine company, we are assuming there is no difference in their performance level. Mu A is nothing but mean of the mean action time of that medicine produced by company A. Mu B is nothing but mean action time produced by company B. So null hypothesis, we are assuming they are equal. Alternative, we are assuming they are not equal. They are not equal. Now, suppose I got that p-value. P-value is 0.05. Okay. And let for a one data p-value 1.05. Generally, if p-value is less, we reject null hypothesis. Now, if your level of test is fixed, suppose we are performing in 95% level, with respect to 95%, this is significant. That means this indicates only 5% evidence in favor of alternative, 95% evidence against this thing. Okay. Now, if p-value is 0.06, what does it mean? Simply, we can assume basically 6% evidence. Basically, this is 6% evidence. 6% evidence is against null hypothesis. So 95.4% evidence is in favor of this thing. So whether you will accept or not, you decide. If you, okay, generally we perform the test in 95% level. With respect to 95% level, if p-value is this thing, we reject null hypothesis. But let p-value is 0.4, okay, sorry. P-value is 0.4, we'll reject null hypothesis. P-value is this thing, we'll accept this thing, or let this is 4.9 and let this is 5.1. So in 90, if it is fixed level, we'll accept here and we'll reject here. But is it justified? So p-value will give, that means 4.9% evidence against only favor of this thing, and here 5.1% evidence only favor for this thing. So in this case, both are equivalent kind of results. So it is better to reject in both cases, or easy in both cases better to accept. Whether we'll accept or not, if it is in 99% level case, you have to accept. So p-value is a smaller means there is a strong evidence against null hypothesis. Suppose you produced myself in a court. All our evidence is going against myself. Let 98% evidence goes against myself. Only 2% evidence in favor of me. So p-value gives the evidence in favor of null hypothesis. So if p-value is less, basically we have to reject null hypothesis. Is it clear?
Yes, sir. Thank you, sir.
Okay. So if no question, so I must convey my sincere thanks to the organizer.
Thank you, sir.
All the participants.
Yes, sir. Thank you, sir. Now we are at the end of the session. On behalf of our university, I would like to thank all our resources and all the panelists present in the today's session, and also our participants for considering us from their busy schedule. I also request our participants kindly fill the feedback form, and we are looking for your active participation for tomorrow's session. Till then, stay safe and stay at home. We are going to close this session. Good night. Thank you.
Sir, we are closing the session. Thank you all. Thank you, sir.